In this goal, we're going to learn a little bit more about saturated solid equilibrium. And this first example we have already done. So there are two different ways to have a saturated solid equilibrium. One way is just to take the solid and stick it in water. And so on the AP test, it'll say something like silver chloride is added to water and it forms a saturated solution. So recall that when you add it to water, you do not have to write the water. And that is because that H2O is on either side of the equation. So because it's on either side of the equation, I can just eliminate it. So I just have the net ionic equation. So it just says that the solid is at equilibrium with each of its ions. Now silver chloride, when you put it into water, it splits up into two ions and it's a 1-to-1 ratio. So if silver is X, then the chloride is also going to be X. And we're given the solubility product constant, the Ksp, as that number. So the first thing I'm going to do to solve this problem, and this is just a review from the previous goal, is I'm going to write a Ksp equation. So remember, the ions are multiplied together in the Ksp equation. Go ahead and solve for the equation. So I'm left with x times x, and then to solve for x, I'm going to square root each side. So I solve that x is equal to 1.33 times 10 to the minus 5. This is also the concentration of the silver ion and the concentration of the chloride, and it's also the solubility. There's another way to make a saturated solution, and this would be to combine two solutions. So let's look at this problem. To a silver chloride solution, I'm going to add drops of silver nitrate. What do I know about each of these solutions? Well, I know that sodium is soluble, and I know that nitrate is soluble. So I know that that is not going to be part of my solid that's going to form. Instead, it's going to be the other ions that are with those soluble ions. So I'm going to have the chlorine combined with the silver. And always write your positive ion first. So my silver is just a +1 and my chlorine is a -1. So when I put it together, I get AgCl, and that is my solid. Here I see those ions that will just also be there present in the solution. They are both soluble. So it's written like this together, but in solution, they're really going to be apart. Now, once that precipitate is formed, that solid can come to a saturated solid equilibrium. This would be my equation. Now, notice it's the same equation as up above. But there's a difference, and that difference is how those ions came about. So in my first example, I know that because I started with the solid and nothing else, I have a 1-to-1 ratio of silver ion to chloride ion. In my second example, because they got there differently, you can have different concentrations. And so they're going to have to give you the concentrations of each of the starting solutions or tell you what the total concentration is of when they're just added together. In this way, you have to be given more information because the precipitate, it comes and arrives differently. So in that precipitation reaction, we started off with a sodium chloride solution, and so they are all present as ions. And then I'm just going to add drop by drop the silver nitrate. And what's going to happen is all the silver is going to combine with the chlorine. And so I'll add another silver, and it'll combine with another one, and I'll add another silver, and we'll combine with another one. Along with the silver does come the nitrate, but that is soluble, so it's just floating around there. So in this equilibrium reaction, we see that silver is our limiting reactant. As soon as the silver adds, it's going to bind up with the chlorine, and I do end up with a little bit of excess chlorine right there that is not used up. And then I have my soluble ions in there. I can write my equation coming to equilibrium. So there's my solid that's formed, and there's my ions that's formed. And then let's look at our information. It says silver nitrate is added to a 0.1 molar concentration of sodium chloride. So I know what the chlorine concentration is. It is a 0.1. So this is an ice chart that I'm starting to form here. Remember, with solids, you don't have to fill in the solid part of the ice chart because solids don't affect equilibrium. And then I start off with 0 of my silver ion. So this is at the beginning of my reaction. Then my silver chloride is going to dissociate. So I'm going to get a little bit more silver ion and a little bit more chlorine. And so when we do our equilibrium, we're going to have an X and a 0.1 plus X. And so just notice that because the chlorine got there first, the silver ion and the chlorine ion do have different concentrations. And this is often called the common ion effect, where I have some sort of ion that's going to influence my equilibrium. Now we know with Le Chatelier's principle that if we add an ion, that's going to shift the equilibrium away. So I am going to end up with more reactants in this type of problem than I would with just the normal dissociation where I start with a solid. So I can expect that the solubility is going to be less. So as if I add it to one side, then I know that the solubility is going to go down. That I can predict. I will have a lower solubility, but let's go ahead and calculate what that solubility will be. I know it doesn't say in this problem, but that is what we're going to solve for right now. So this is going to be done the same way. So write your Ksp. Let's put in our values. If I looked at this and I did my algebra, I would, when I distribute, I would have 0.1x and I would have x squared, and this would have to be solved with a quadratic equation. So instead, I am going to look at what my Ksp is, and my Ksp is times 10 to the minus 10, and that's pretty small. So I am going to take the shortcut. So taking the shortcut, this means that I'm going to eliminate this plus x, because I know the x is going to be tiny. And so let's go ahead and just solve it. I'm going to divide each side by 0.1, and I get x is equal to 1.78 times 10 to the minus 9. X is what the silver is. And so in this problem, this is my solubility. And if I look at what the solubility would be if I just started with the solid, remember my x in that other case, I got 1.33 times 10 to the minus 5. So you can see that Le Chatelier's principle, adding that chloride ion there, it does decrease the solubility, because now I have a 10 to the minus 9 when before, when I start with the solid, I just had a 10 to the minus 5. So you can think through this and you can also solve for what it is. You can go back and just double check that having x be tiny and eliminating it won't change your calculation. And so let's just double check that. So if I took 0.1 and I minused a 1.78 times 10 to the minus 9, I know that that is really not going to affect anything. So $1 million minus a nickel is still going to be $1 million. So it's not going to really affect how much money you have, nor will it affect our how much ion we have. So let's do another calculation. This says calcium fluoride is placed into pure water and a saturated solution forms, and there's our Ksp. Solve the solubility. So again, we're starting here with just our solid. Calcium is a +2. Fluorine is a -1, so I put them together, I have a 1:2 ratio. And we have a saturated solution, so let's go ahead and write out all those ions. Let's just double check that we have it balanced. And I see that I do need to put a 2 here in front of the fluoride ion. Where the fluoride ion is just a -1, then it's a 1:2 ratio. So let's go ahead and write our formula. Before we put our numbers in, let's figure out what those ions are going to be. So I know that if calcium is X, then I know that the fluoride will be 2X. So those are the values I'm going to put into my formula. So it might look a little weird where you have a 2x squared, but that is the correct answer. So I'm going to divide by 4, and then I'm going to take the cube root, and I get x is equal to 2.4 times 10 to the minus 4. So this is the solubility. So remember, the solubility is if you just have one of them. So let's compare this to if our ions arrived a different way. So now let's calculate the solubility if I have a common ion. So my formula is going to be the same. I still have calcium fluoride, but this time it is placed in a sodium fluoride solution. So there's my equation, and I know that at the start for my ice chart that I'm going to have a 0.025 concentration and then 0 of the calcium. I know that once the solid is formed, then it's going to come to equilibrium. So I'm going to get a little bit of calcium and a little bit of the fluoride ion. And make sure you put in your ratios correctly. This should be plus 2x. And then at equilibrium, I'm going to have x. This is going to be 2x plus 0.025. And then I can write my Ksp equation. Don't skip your formula step. I'm going to assume the shortcut. So I'm going to cross out this 2x, just assuming that it's going to be tiny because x is tiny. So I get 6.25 times 10 to the minus 4x. Divide each side by that number, and I get x is equal to 6.4 times 10 to the minus 8. You can just double check. You should have an order are 3 orders of magnitude between your Ksp and what your X is if you take that tiny rule, and it looks like that it will be just fine here. You also can take this number and plug it back into your original formula. So I would have 2x plus 0.025, and just kind of double check that that's not really going to affect the solubility, and it doesn't affect it. So what is this X? This is our new solubility if I have a common ion. And you can see that it is much less than it would be if I just started out as a solid. And that has to do with Le Chatelier's principle, because if you add to one side, it shifts it away. One thing I failed to mention that you can figure out what that fluoride ion concentration is. We see that when you go in and solve everything, it is just that 0.025, and that is because that was my original concentration, and again, X is really super tiny. So that's one thing you can do, is solve for both of the ions. But if you're starting out with a certain concentration of ion, chances are it might be the same. But go ahead and work out the math just to make sure it's not different. Let's do this sample AP question. Answer the following questions about the solubility of silver iodide, and it gives us the Ksp. First of all, it wants us to write a balanced chemical equation for the dissolution of silver iodide in pure water. Remember, water will be on both sides of the equation, so you don't need to write it. It is optional to put the species, but I did put that a solid goes into 2 aqueous ions. And I know that silver is always a +1, and iodide is a halogen, and so it's always a -1. So that's why I need to put those charges there. If you don't put those charges there of the ions, then it's wrong. And again, you don't see water in here because next we're going to calculate the molar solubility, and it looks like it's going to be put into a solution of silver nitrate. So this is my common ion, and I'm just going to transfer the equation down and then do an ice chart. I separate out my reactants and my products, and know that because this is a solid, nothing should be right there. We only put aqueous and gaseous species into equilibrium constant expressions, or these problems. Put in what we know. So we know that the silver is a 0.01 molar concentration, and we're going to start off with 0 of the iodide. And then we know that our silver iodide is going to dissociate. So they will both be a +X. It's a 1-to-1 ratio. And then bring everything down. So I'm going to have 0.01 plus X and a +X. I'm going to write my Ksp equation. And replace what we know. And then looking at the algebra for this, I'm going to have to distribute the X. So I'm going to end up with an X 0.01, 0.01x times plus an x squared. And so I'm going to have to use the quadratic equation to solve this. Remember, on the AP exam, there should never be the quadratic equation. And so what I'm going to do is I'm just going to simplify this. So I'm going to assume that x is tiny. And so I'm going to get rid of this one right here. And that's because 0.01 plus a very, very, very tiny number is going to be 0.01. So let me just cross that out. Down here, so I'm going to end up with 0.01x is equal to my Ksp. I'm going to divide each side by 0.01, and I get x is equal to 10 to the minus 15. And I end up with 1.5 times 10 to the minus 14. Replace this back up here. So we get the concentration of the iodine is what X is. And this is our molar solubility. And because I start off with already some silver in the solution, I want to look at the other ion. So this is going to be my answer. I could calculate the silver ion. I'm going to get 0.01 plus 1.5 times 10 to the minus 14. So again, this is a much larger number added to a very smaller number, and I am going to get a 0.01 molar concentration for the silver ion. And so you can see that that little saying that X is tiny, it's not going to affect your answer, but it's going to help us to solve it easier. How can we predict whether or not two solutions will form a precipitate? We can find what's called the Qsp, the solubility product quotient. It just means given the numbers that we know or the concentrations that we know at that moment, we can find the Q. Remember, the K is when we're at equilibrium. We use the Q if we know that we're not at equilibrium. And so we're just trying to make a judgment call whenever we use Q. The Qsp is solved the same way as the Ksp. It's products over reactants. And remember, there's no reactants because the reactant is a solid. And so here we can see on this one, there are some initial concentrations that will be given, and then we can make the judgment call of whether a precipitation reaction occurs. If our Q is bigger than K, then that means we will get a precipitation reaction. So the concentration will be high enough that we will find that a solid will be formed. So this is used when you're dissolving a solid into water and you just want to know if it's going to be a saturated solution. And so that's starting with a solid, but we are going to see later on you could start with two solutions that then form a solid that then dissociate into water as a saturated solution equilibrium. And if our Q is less than Ksp, then that means that there is not a high enough concentration for that solid to settle out at the bottom or for a solid to form in the first place. So in this problem, I have two solutions that I am going to dump together into one vessel. And I'm going to see if a precipitation forms. So that's the whole idea of this. In my first one, I have a 0.001 sodium iodide. And in my next one, I have, boy, that's a lot of zeros. I'm going to have 1 times 10 to the minus 9 molar concentration, and it's silver nitrate. So we're wondering, is a precipitant going to be formed? And we want to write a saturated solution equation. So what is that solid that's going to be formed? So when I look at the sodium iodide, I need to go back to my solubility rules. And when I look at sodium iodide, I know that Na plus is always soluble. So I know that that is not going to be part of my solid. Instead, it's the iodide, the I minus, that is going to be part of my solid. And then let's look at the other one. So I have silver nitrate, and I know there's a solubility rule about nitrate. So I know nitrate cannot form the solid because it's always soluble. So that means the silver ion, that is going to form my solid. So silver ion and iodide ion, I'm going to get AgI, and we looked at this one before. And I'm going to dissociate it. Again, it's optional to put the species in. And then I'm going to look at the concentrations. So I know what the concentrations are before they're poured together. As soon as I pour them together in that moment, I've actually diluted their concentrations. I'm starting with 500 milliliters for both of them. So I know that when I dump them together, I'm going to dilute it by half. 500 milliliters plus 500 milliliters will be 1,000 milliliters. And so my moles is going to stay the same, but I am going to dilute it. You can find the moles and then divide it by the liters, but I think for this one, I am just going to take a little shortcut and say 0.001 divided by 2. I'm going to get 0.0005 molar concentration. And for my iodine, I'm going to have 1 times 10 to the minus 9 divided by 2. And this is because I'm doubling the volume from what it was before. So I have 5 times 10 to the minus 10 molar concentration. There's my diluted concentrations, and they are going to be what I'm going to put into my QSP. And I'm using my QSP because I am trying to figure out if it will form a precipitate, so if a solid will form from dumping these two solutions together. So let's put in our values. And I get QSP equals 2.5 times 10 to the minus 12. And so we're going to compare that to the KSP. And we see that the QSP is a lot bigger than the KSP. So the answer is yes, we will form a precipitation. And that is because our concentrations are large enough that they will precipitate out. We will form the solid, and then we will come to that solid equilibrium. I think I might have entered in my numbers incorrectly because I'm off by a -1, but we still see that there is a precipitation reaction. Let's try this reaction. So I have B and Z are unknown, but they are with nitrate and with sodium. And remember, nitrates are always soluble, and so are sodium ion compounds. And so these are both mixed together. And it says, what is the solid formed? And after mixing, it is found that we have a given concentration of both of those. And so in this one, because it is telling us those concentrations after mixing, I don't have to find the initial concentration because they're given to me. So again, this is where the ions are coming a different way. If I just took my BZ solid and put it into equilibrium, I would see that these guys are the same concentration. But in this case, both the B and the Z arrive a different way. They come separately, so your concentrations will not be the same in this one. So first of all, let's write our dissociation equation, and then let's write our QSP, and we can put in those initial concentrations, and they're given to us. And doing the math really quickly, we have 1 times 10 to the minus 14 is what our QSP is, and we can compare it to our KSP, and we find that our QSP is a lot less than our KSP, and so this one would not form a precipitant. So there would be no solid formed. Let's go ahead and change our values. So what if after mixing, these are my concentrations? So let's go ahead and put those values in. So I get 1 times 10 to the minus 11 as my QSP, and again compare it to the KSP. And I still see that my QSP is a lot less than my KSP. So again, still no precipitation. The concentrations have to be large enough to be bigger than that KSP to precipitate. Let's look at this next set. Put my numbers in, and I get 1 times 10 to the minus 10. So finally I see that this is bigger than the KSP. So I do have a precipitant that formed. And then we have one more example, and because again they're 1 to 1, I'm just going to multiply these two together, and I'm going to get 1 times 10 to the minus 8. So that is way bigger than my 1 times 10 to the minus 10. So for sure this one will form lots of solid. So this is a way to form your solid that then goes into equilibrium, and the questions they will always ask is if it will form a precipitant. So in this problem I have two solutions, and I'm going to form a precipitate by pouring them together, and then a solid will form. Well, I need to find out what solid is going to form. So let's look at each of the formula and figure out whether the cation or the anion will form the solid. So cerium nitrate, I'm going to think of my solubility rules. Nitrates are always soluble. So I know that this is not going to be part of my solid. Instead, I know that the cerium is. So for sure, I'm going to have some cerium ions in there. Potassium is always soluble. So this is not going to form a precipitate because it's always going to be able to dissolve. So this one is not a part of my solid. Instead, it's going to be my iodate. So I know I'm going to have my iodate in that solid. So it will be cerium iodate is this salt or the solid form. Write your equation. Cerium is a +3 because it has 3 nitrates. Potassium is a +1, so that means the iodate must be a -1. Putting them together, I get cerium iodate. There should be 3 iodates. So I need to balance this by putting a 3 right there. So this is what happens when I put them together and I form a solid. There's my solid that's formed. Once the solid is formed, that solid can then dissolve back into solution, and it can come to equilibrium. So let's write our equilibrium solubility product equation. Essentially, we just turn it around again, but we see that we start off with a solid and it breaks up into its ions. From this, at equilibrium, I can write my Qsp. Next, I want to find my initial concentrations of both the cerium and the iodate. To do this, I'm going to be looking at the information that they give me. And they tell me that cerium, I have 350 milliliters, and I have 4 × 10⁻³ molarity is my initial concentration. So from this, I'm going to find the moles. So I changed my units here. I changed the molarity to moles per liter, and I changed my milliliters to liters. That way, when I multiply them together, the liters will cancel, and I will be left with my moles. And I get 0.03 moles. Then I'm going to take, after I find my moles, I'm going to divide by the total volume of when I pour both the solutions in. And when I divide it, I get 0.00286 as my concentration of my cerium. So we're going to do the same thing, but now with the iodate, I'll first find the moles, and then I'll divide it by the total liters so that I can find that the instant that they're poured together, I can find that concentration. And I get 0.006 moles. Then I'm going to divide that by the total. And my final answer, I get 0.00571 as my molar concentration of my iodate. So now I'm going to take these two values and I'm going to plug them into my Qsp equation right here. So the last step is just to plug in each of these values into my Qsp. And remember, it's cubed. My final answer is 5.32 × 10⁻10. So this is the Qsp. And I'm going to compare it to the Ksp, which is 1.9 × 10⁻10. So I can see that the Q is bigger. And because of this, I can say yes, it will form a precipitate. So again, find your initial values, which takes some math to get there. Plug it into your Qsp, and then evaluate if it's big enough to form precipitate. If the Qsp is bigger than the Ksp, you will form a precipitate.